Okay, so in the first part of this experiment, we wanted to do two different things. First, we wanted to make a sodium hydroxide solution of a certain concentration using a solution that we have on the bench tops that are 6.0 molar. So basically, we're going to water it down. We have two different equations that we can use to figure out how much of that more concentrated solution we need. The first one is M1 V1 is equal to M2 times V2. So M stands for molarity in units of moles per liter, and volume can be in either liters or milliliters. You may also see this equation as C1 V1 equals C2 V2. C stands for concentration, which is the exact same thing as molarity. Okay, so let's start plugging into our equation. As we said, on the bench tops we have a 6.0 molar sodium hydroxide solution, but what we want is a 0.2 molar solution. So let's plug in what we have and what we want. So what we have is a 6.0 molar sodium hydroxide solution. We don't know the volume that we need of that solution, so I'm going to leave that as V1. The concentration we want on the other side of the equation is 0.20 molar, and we want to make a 500 milliliter solution. So to isolate V1, we need to divide by 6.0 molar, divide by 6.0 molar on the other side, so those cancel. V1 is going to be equal to approximately 16.67 milliliters. So since we don't have to be so exact with this measurement, we're going to say that this is close to 20 milliliters. So what you do to make your solution is, in lab, you measure out in your graduated cylinder approximately 20 milliliters of the 6.0 molar sodium hydroxide solution provided on the bench tops, and you have a bottle that's exactly 500 milliliters. So you're going to pour the base, the sodium hydroxide solution, into the bottle and fill the rest up with deionized water. The next part of our experiment is we've made a solution. Now we need to figure out the exact concentration. It should be around 0.20 molar, but since we're going to be using that concentration in the rest of the experiment, we need to actually figure out what it is. That brings us to the next part of the experiment. And the way we're going to do that is using something called a titration. So a titration is when you have a known amount of one thing and you're trying to figure out the either concentration or amount of another substance. So we're going to be starting with an acid called potassium hydrogen phthalate. So this whole thing is phthalate. And it's usually abbreviated as KHP. So this hydrogen is acidic and it's going to react with our sodium hydroxide solutions, a base. So since it's an acid-base reaction, we're going to form a salt and we form water. So the important part about the first part of this experiment is we're using a known amount of KHP to figure out the molarity, which is the same as concentration of our sodium hydroxide solutions. And we're going to be doing 3 different trials because we're looking at precision. How reproducible are our results? So I'm going to go through the calculations for the first trial, and then you'll be able to do the rest on your own. To measure out the mass of KHP, what you did was you took an Erlenmeyer flask, zeroed it on the balance, and then you can add your solid KHP straight to the Erlenmeyer flask, and what we got was 1.136 grams. The next thing we need to do is dissolve it in water because it's a solid, and we need to add an indicator. So we're adding an acid and we're adding a base. When we reach what's called the equivalence point, the number of moles of the acid, the KHP, are going to be equal to the moles of sodium hydroxide. But we need an indicator to know when we hit this equivalence point. So any sodium hydroxide we add after that equivalence point makes our solution basic, and we can use a phenolphthalein indicator to visualize this. So you'll see a slight pink color. To get accurate volume readings of the amount of sodium hydroxide we're using, we're going to use a burette. And 2 important pieces of information we need to take down are the initial reading of the burette and the final reading of the burette. Remember that we always need 2 places after the decimal when we're reading a burette, If it's right on the line, it's going to end with a 0. If it's anywhere in between the small lines, it's going to end with a 5. And here are the measurements that we got. The next thing we want to do is calculate the amount of sodium hydroxide we actually used based on our burette readings. So we're going to always take our final reading minus our initial burette reading to get the volume of sodium hydroxide we added. So 37.50 milliliters, and we're going to subtract 11.50 milliliters. And what you get is 26.00 milliliters that you added. Remember that we're doing subtraction, so 2 places after the decimal should be in our answer. We know that units of concentration are moles per liter, so we can't just leave it in milliliters. We have to convert to liters. We know that there are 1,000 milliliters in every liter, so we need to move the decimal place 3 times. So when we convert to liters, we get 0.02600 liters. Notice that we still have 4 significant figures. We started with 4, so we still need to end with 4. The other part of our concentration or molarity calculation is we need to figure out the moles of sodium hydroxide, which we don't know, but we can figure out using the amount of KHP acid that we started with. At the beginning of the experiment, we weighed out 1.136 grams of KHP. If we follow our roadmap, the next thing we can go to is moles of KHP using the molar mass, which is 204.22 grams of KHP in every 1 mole of KHP. We need to go back to our balanced equation to figure out the mole ratio of those two. From our balanced equation, we get that for every 1 mole of KHP, we're going to react it with 1 mole of sodium hydroxide. Let's put that in our problem. For every 1 mole of KHP, we react it with 1 mole of sodium hydroxide. So now we're in moles of sodium hydroxide, and if you calculate that out, what you should get is 0.005563 moles of sodium hydroxide. Keep in mind again, we started with 4 significant figures, so we need to end with 4 significant figures. Last step of our problem. We have moles and liters of sodium hydroxide, so now we can figure out the concentration. We need to take the moles we got in step 6, so 0.005563 moles of sodium hydroxide. And we need to divide by the volume, and we have to make sure it's in liters, 0.02600 liters. We have 4 significant figures on the top, 4 on the bottom, so our answer should have 4. Our final concentration is 0.2140 molar. Remember that molar is the same as moles per liter. You're going to do 3 different trials, and since we're looking at precision, we want to make sure that our concentrations are fairly close once we calculate them. So if your 3 concentrations that you calculate differ more than 0.005 molar, you need to repeat the experiment and do another titration. Once you have 3 titrations that are close enough, we want to figure out an average. So the average value is what we're actually going to use in the other parts of the experiment. An average is always going to be the sum of the trial values divided by the number of trials. So if we get these values for our 3 trials, let's calculate the average. We have 0.2140 molar plus 0.2148 molar plus 0.2122 molar. We have 3 trials, so we're going to divide by 3. Remember that the 3 doesn't count for significant figures because it's an exact number. We know we had exactly 3 trials. If you calculate that, your average will be 0.2137 molar. This is the value that you're going to use in parts 2 and 3 of this experiment as your concentration of your sodium hydroxide solution.